Hi everyone, in this video we're going to talk about how to set up open loop boost control on the modular ECUs. Now in open loop mode, it means that the ECU has a duty cycle which it feeds to the solenoid valve, and whatever boost that generates is what you get. Now a lot of tuners like this because it's very simple to set up, but it does have its limitations, so let's talk about the physical hardware that we have to deal with first of all. The first thing I'm going to talk about is the mechanical side of boost control. Now the reason I'm going to start with this is that a lot of times people ask about how to do boost control settings or help with diagnosing a boost control problem when they think it's an ECU setting problem, when actually it's because they don't understand the mechanical system. So if you do understand mechanical boost control systems, then please skip ahead. Now we know that exhaust gas comes out of the engine and spins the turbine, and therefore to control the amount of boost that we're going to generate, we need to have a wastegate which allows exhaust gas to bypass the turbine. Now the wastegate is a flap or some other sort of valve which is controlled by an actuator. Now although in theory it should be possible to make a butterfly style where the pressure on one side doesn't actually force the door open or closed, in practice every one that I've seen is either a valve which lifts off a seat and therefore exhaust pressure tends to keep it open, or the other type is a flap, a trapdoor style thing, which again increased exhaust manifold pressure tends to force the door open. Now this is an undesirable effect, but it's one that every wastegate that I've seen anyway has, so we need to bear it in mind. Now apart from this undesired effect, the real thing that's supposed to control the wastegate being open or shut is the actuator, and the actuator is a servo diaphragm where you have pressure on each side of the diaphragm, and the pressure difference across the diaphragm actually controls how much force is activated. Now there's also a spring which holds the wastegate shut, and that spring has a fair bit of preload on it, and that preload is called the cracking pressure if you like, because once you exceed enough boost to overcome the preload of the spring, then the actuator rod starts to move and the wastegate itself starts to open. Now on some actuators they have both sides of the diaphragm have got are sealed and they have ports going to them, so you can control the pressure to either side individually. And on some of them there's only a port on one side, which is the side that you need to put pressure into to make it open, and the other side is just open to the atmosphere. And these are normally called single port or dual port actuators. There are other differences with actuators as well. Some wastegates are liquid cooled, and some of the turbo smart ones actually have a rod that sticks out, and you can get a position sensor to actually measure the position of the gate to help with diagnosis. Now let's talk about the most basic system, which is a single port actuator. In this system, the single port is fed with pressure from the boosted air exiting the compressor, and once that pressure exceeds the amount that's required to overcome the preload of the spring, the rod starts to move and the flap door opens. Now when the door starts to open, exhaust gas starts to bypass the turbine, and the turbo then has a bit less pressure available with which to build more boost. So it ends up in a position where it regulates its own boost in that way. Now there are several ways that people control the boost on these type systems, but we'll just talk about the 3-port solenoid method. So in this method you have a 3-port solenoid where you have a common port which is normally connected to the normally connected port, so air just flows straight through it, and then when the solenoid's energized, the common port connects to the normally closed port instead. So in this case what you do is connect the actuator to the common port, and then the normally connected port connects to the boost source, so the exit of the compressor. So that way when the solenoid's off, the air just flows straight through and you end up having the standard actuator boost. Now the normally closed port of the valve vents to atmosphere, so if you give the solenoid 100% duty cycle and turn it on completely, then the actuator actually doesn't see any boost at all, and in theory then remains completely shut. So that way you can adjust the boost pressure anywhere from the wastegate boost level up to infinity, or as much as the turbocharger will make. And by pulse width modulating it, you can get somewhere in between. So for example, if you have a 10 psi spring in the actuator, then at 0% duty cycle you'll end up with 10 psi of boost, or slightly more because it has to open a little bit. If you give the solenoid 50% duty cycle, then that means that half the time the actuator is seeing pressure from the boost source, which is the compressor exit, and half the time it's seeing the outside air. So that means that the boost source must be at 20 psi, so that the average pressure that the actuator sees is 10 psi, which is what it's set to. So that means that with 50% duty cycle on the valve, you'll end up with double the boost of the spring. Another example is if you set the duty cycle to 25%, you'd end up with 13 psi of boost. Now in general you'd pulse width modulate the solenoid valve at about 30 Hz, that's what they tend to like. Now let's talk about one of the limitations of this system. As I mentioned before, exhaust back pressure tends to force the wastegate open. So unless the diaphragm in the actuator is very large compared to the area of the wastegate, then at higher boost levels and at higher engine speeds where there's more back pressure as well, the exhaust back pressure tends to force the wastegate open. And in practice that limits the amount of boost that you can run with this sort of system. It also has the effect that if you just run a constant duty cycle to the solenoid valve, even though the sums I gave you before would suggest that that would give you a constant boost, you'd actually find that the boost actually decreases at higher RPM because of the increased exhaust back pressure. Now, TurboSmart have actually come out with a solution to this, which is called the IWG. It's basically an aftermarket replacement for an actuator from an internal wastegate type turbocharger, and this differs from the factory one because it has a much larger diaphragm area, which means that the boost regulation is better because it has more ability to overcome the force from the exhaust back pressure pushing the wastegate open. So this makes the boost pressure more consistent and more predictable, and also increases the maximum amount of boost that you can run with this configuration. Now I'm just going to talk about a common mistake. I believe it's a mistake that people make, which is to source the actuator reference pressure from the inlet manifold instead of from the compressor exit or some other part before the throttle body. So what it means is that the actuator will try to regulate the pressure that it sees at its input port, because that's what closed loop systems do. And so if you take the pressure reference from the inlet manifold instead, then even when you're at part throttle, the actuator will still try and get the inlet manifold to that same target boost. So for example, if you're at part throttle and you've got a 10 psi spring, because that's what we've been using as an example, then the driver may only want 0 psi of boost, right, because they're on part throttle. But the actuator is going to be closed at that point, so the wastegate will be shut. That will increase the boost of the turbocharger. So the turbo may end up producing, say, 20 psi of boost in order to achieve 10 psi of boost in the manifold with the partly closed throttle. Now this has got two bad effects. One of them is that it actually undoes what the driver's trying to do. So for a wide range of throttle openings, you'll end up with the same boost pressure because the actuator's closing the loop to undo what the driver's trying to do with the pedal. The other potential problem is that if the turbo has to spin very fast to achieve that boost level with the partially closed throttle, then when the driver does suddenly put their foot down, you could get an overboost condition, or the power could pick up very quickly and become a problem for the driver. Now, as well as the single port IWG that I mentioned before, TurboSmart also have a dual port version of the IWG, where both sides of the diaphragm have got ports on them, so you can control the pressure to each side individually. With the single port, one of them is always open to the atmosphere, so the other side is the one that you have to get to your target spring pressure. So with the dual port actuator, the connection is normally different. The port which you would normally put pressure into to get the wastegate to open would actually normally be connected to the boost pressure all the time instead of through a valve. And then the reference port, if you like, which is the one that you'd apply pressure to close, which would normally be vented to atmosphere on a single port actuator, instead goes to a 3-port valve, but the connections are opposite on the valve compared to what they'd be on a single port. So the way to connect it normally is such that the reference port on the actuator normally goes straight to atmosphere, and when the solenoid's energized, it actually connects to the boost pressure instead. So this way the mathematics works out the same, and the duty cycles end up being roughly the same as with a single port actuator, but it means that there's a lot more pressure available to allow the actuator to fight against the back pressure from the exhaust. So this allows you to go to high boost levels and do it more predictably than with a single port actuator. Now, normally this allows you to get up to about double the spring pressure of whatever the spring is that you've got in the actuator. Now, this method also applies equally well to external wastegates. The construction of an external wastegate is normally quite different, and you have the bottom port is the one that needs pressure on it to force it to open, and the top port is the reference, if you like, which on a single port configuration will be open to the atmosphere, and on a dual port configuration would be the one that gets switched between atmosphere and boost pressure. There's a third connection type which I'll just describe. And this is basically a hybrid of the two that I said earlier. So you can think of it as having two separate 3-port valves. One of them goes to the reference port on the actuator, and the other one goes to the pressure port on the actuator. And they're configured in the same way that the previous two examples are described. So when the power is off, then the pressure port sees the boost pressure from the compressor, and the reference port sees the atmospheric pressure. And then when both solenoids are on, it's the other way around. So this way the reference port sees all the boost pressure and the pressure port actually sees atmospheric pressure. So what this means is that there's a much wider range of pressure differentials that you can apply to the wastegate itself, and this makes it a lot easier to overcome higher exhaust back pressure, pushing the wastegate open. So this allows you to get a much higher range of boost levels with the same spring in the gate. You can also buy these 4-port valves, which conceptually are the same as two 3-port valves in the one package to make it a lot simpler to install. And electrically, if you're going to run the 2 3-port valves, you just connect them in parallel off the same output from the ECU. Now, the limiting factor on a 4-port valve configuration is when the exhaust back pressure plus the spring pressure of whatever you've got in the actuator becomes more than the boost pressure that you're trying to achieve. And in that situation, the best way to do it is with an external pressure source, the most popular way being a carbon dioxide bottle. Now that we've talked about the mechanical system, we can talk about the ECU settings and how to set it up. The first thing to understand is that the ECU uses many variables to work out what the duty cycle should be. There's a basic map, but there are also additional limits that you can apply for ethanol content, the current transmission gear, and digital inputs. All these settings are found in the Tuning Air section in the Eugene software, and then there's a subsection there called Boost Control Settings. Now, first of all, this article describes how to set it up in open loop mode, which means we're going to enter duty cycles directly, and then we're going to tune them to get to the required level of boost. So for this, you should select open loop mode, duty cycle only, as the boost control mode. Secondly, you can select whether to use dual maps. So for example, if you want to have 2 separate maps that the driver can select with a switch, where you can have duty cycle mapped against throttle position and RPM arbitrarily, then you'll need to enable the dual boost map mode. And then you'll have 2 separate duty cycle maps to change. If you want to use a dual boost map mode, then you'll also need to wire up a digital input to a switch, and you'll need to configure that digital input to be boost setting 1, and then when the switch is enabled, the second boost map will be used. Secondly, the ECU is only going to activate the wastegate duty cycle output when certain conditions are met, such as minimum throttle position and minimum manifold pressure. Normally you'd set up these conditions so that they don't happen on cruise. So for example, you could set the minimum manifold pressure to be slightly above atmospheric, and throttle position would normally set to be a minimum of about 30% or something like that. Now, you can also set these up in the map as well. If you just have 0% below 30% TPS, then you'd achieve the same thing. A duty cycle limit is a percentage that you can enter, and the ECU won't exceed that duty cycle percentage. Now, in a properly configured and tuned system, there's no reason for that not to be 100%, but it's there as a safety function or a way of conveniently trying different duty cycles without rewriting entire maps. Now, you'll also need to set up an output to drive either a 3-port or a 4-port MAC valve. Now, this should be an auxiliary output, or in a modular ECU, you can use an unused injector output instead. The other side of the valve should be connected to an ignition switch 12-volt supply, and the output in the settings needs to be configured as wastegate duty cycle 1, PWM enabled, and as I said before, normally 30 Hz is what you drive them with. Now, you can run 2 or 4 valves off a single output. They don't draw that much current. And even though you see wastegate duty cycle 2 option available, the only reason you'd use it is on a dual wastegate system where you've got 2 separate controls and you're doing it closed loop. For example, on a 300ZX or a V12 where you've got 2 separate turbochargers and 2 separate inlet manifolds, and you need to control the 2 independently. Once you've set up those settings, you can adjust the duty cycle in the boost control duty cycle map. In the single map mode, you'll just have duty cycle map 1, but in a separate map mode, you'll have maps 1 and 2, which you can adjust individually. The axes of these maps are throttle position and RPM, and just like all the other maps in the modular ECUs, you can remove and insert columns and rows as you like. Now, there's another correction map in there, which hopefully you won't need to adjust, but it's there in case you do, which is a correction for air temperature and manifold pressure. So in theory, this map should all be at 0, but on some cars found that lower air temperatures with the same duty cycle, they end up producing more boost. And so in this case, you could enter a negative value at the lower air temperatures, so that percentage gets subtracted from the duty cycle. Now, the vertical axis of this map is manifold pressure. So if you wanted to, you could actually use this as a semi-closed loop function if you like. I know that some tuners like to do this where they have a slight correction to the duty cycle based on the manifold pressure. The downside of this over using a proper closed loop system is, of course, that this map doesn't know where the target is or what you're trying to achieve. Now, mathematically, this is similar to a proportional controller, so it's still possible to make it hunt or oscillate if you make the ramp too aggressive. Now, the next thing we have to consider is limits. So the ECU can have boost duty cycle limits based on ethanol content, which transmission gear is enabled, and an external digital input switch. If you go to the limits page in the software, you'll see that each of these has got a separate enable function. Now, ethanol content is the first one, and if you enable it, you'll find that there's a map for ethanol content on one axis and the maximum duty cycle on the other axis. So if, for example, you enter 30% as the maximum duty cycle limit at the current ethanol percentage, and you've got 50% in the base duty cycle map, then the ECU will only give 30% to the wastegate control valve. The exception to this is if you push the push to pass switch, but I'll describe that a little bit later. The next input is the gear-based input. So in this situation, you can have a different column there for each gear. And again, the percentages clip the maximum duty cycle percentage going to the wastegate control valve. And the final limit function is used for an external boost switch. So you can have up to 4 separate settings on an external boost switch, and the way to use this is with 2 separate digital inputs. One must be configured as boost setting 1 and one must be configured as boost setting 2. They're done in binary, so if both of those inputs are off, then the boost switch is at 0. If boost setting 1 is on, then boost setting is 1. If boost setting 2 is on, then it's 2, and if both are on, then it's 3. So this table can have a table of different duty cycle limits based on the different boost switches. So if you want it to use the actual value that's in the map, then you'd set the maximum value to 100%. And otherwise, if you set it to a lower percentage, then that's what the duty cycle will be limited to. Now, on some systems, having a fixed duty cycle might actually make the boost not constant when you actually want it to be constant. For example, if there's a boost taper due to the actuator not being strong enough, like I described earlier. So in that sort of situation, then one of the target boost modes will probably be more appropriate for what you're doing. Now, the final setting that I'll talk about is the push to pass button. So this sort of reminds me of the Roger Ramjet cartoon where he takes the proton pill that gives him the strength of 20 atom bombs for a period of 20 seconds. But in this configuration, you can actually set the amount of time. It doesn't have to be 20 seconds. And instead of the 20 atom bombs, you can select what the duty cycle is going to be. So this basically gives you an increased duty cycle for a certain amount of time. And it's used for short overtaking periods in endurance racing. That's basically the function for it. It's also called scramble boost by some people. Now, please also note that the push to pass function overrides all of the inputs that you may otherwise set in the other gear inputs or ethanol limits or that sort of thing. The only thing it doesn't override is the maximum duty cycle limit that would normally be set to 100%. Thank you very much.